Hey, it's Mr. Lum again, and today we're going to do some more acid-base chemistry, and we're going to be looking at the Brønsted-Lowry theory or definition of acids and bases. So this definition said an acid is something that donates a proton to other substances, and if we remember, a proton is just another way of saying hydrogen ion. So a proton is also the same as H+. So an acid donates a proton to other substances, or in other words, donates H+ to other substances, while a base is something that accepts a proton from other substances. So let's look at an example of this, and why we like to use the Brønsted-Lowry theory of acids and bases over the previous one, the Arrhenius theory, is because this takes into account a lot of equilibrium reactions. But let's take a look at something. So here we have HS minus plus H2PO4 minus, and that is going to make H2S and HPO4 2-. So we see here, here is an acid-base reaction right here. So HS right here, it goes from HS and becomes H2S. So in order for HS to become H2S, it had to gain a proton. It had to gain a hydrogen. Okay? So it gained an H+, and that's why it lost its negative charge right here, and it also gained one more H. So since it gained a proton, this is a base. This is a base because it gained a proton. Okay, or in other words, accepted a proton. Gained H+. Now H2PO4 lost a proton, or in other words, donated a proton and became HPO4 2-. So it lost one proton. So this, since it lost a proton or donated a proton, this is an acid because it lose an H+. Okay? So let's take another look at another one right here. HCl plus something that we did the last time, plus water, and that makes H3O plus and Cl minus. So HCl becomes Cl minus over here, and in order for HCl to become Cl minus, it had to lose an H+. So this loses an H+, and therefore, since it loses an H+, HCl is a acid. Now H2O became H3O+, and therefore it had to gain an H+, and therefore this is a base. Now that's a little bit different. Water right here is a base. Now water isn't necessarily basic, having a pH that is greater than 7. All it means is that water here is acting as a base. Water is acting as a base by accepting protons. Okay, so water can be bases. Now waters can also be acids too, and we're going to look more into that a little bit later. Okay, some more definitions right here. The first one is a monoprotic acid, and a monoprotic acid is something that can give one proton. A diprotic means can give 2 protons, triprotic 3, and poly, the word poly just means more than 1. So again, hopefully we memorize what mono means. Mono means 1, di 2, tri 3, and poly just means many. So let's take a look and classify some of these acids right here as being mono, di, tri, or polyprotic. Okay, so let's start with this one right here, H3PO4. So this has 3 protons that it is capable of donating. Since it has 3 protons that it is capable of donating, this is triprotic. This is a triprotic acid. But since it has more than 1, you can also say that this is a polyprotic acid. So H3PO4 is a triprotic acid, and you could also say it's a polyprotic acid. So polyprotic as well. Now HCl only has 1 proton it can give. HCl can only give up 1 proton, and therefore it is a monoprotic acid. Again, HCN can only give up 1 proton, so therefore again it's a monoprotic. Now, can you do these last 2 right here? Hopefully you came up with something like this. It has 2 hydrogens or 2 protons that it can donate, and therefore it is diprotic. But again, since it's more than 1, we can also call it polyprotic. And here, this can donate up to 4 protons, and so this is a polyprotic acid. Okay, so a little definition of mono, di, tri, and polyprotic acids. Okay, now we're going to work on another definition, which is called amphiprotic. Now, amphi means both. Okay, so amphiprotic means a substance that can act as an acid or a base. And if it can act as an acid or a base, then we call it an amphiprotic. So things that are amphiprotic, well, water is amphiprotic, and how to tell if something is amphiprotic is a substance with a negative charge and has a hydrogen that can be removed. Okay, so if it has to have 2 things, it has to have a negative charge and a free hydrogen, and then it can be amphiprotic. It has to have negative charge and a free hydrogen, or it can just simply be water, and that's amphiprotic. So water is always amphiprotic, and we'll look at why. So here is H2SO3, sulfurous acid, combining with water, and that is going to make H2SO3 will donate a proton to H2O and make H3O plus, and it's also going to make HSO3 minus. Now, let's look at what HSO3 right here is doing here. So, or H2SO3. Now, this is donating a proton, so therefore this is acting as an acid, and H2O is accepting a proton, and so therefore this is acting as a base. Okay. Now, is H2SO3 amphiprotic? And the answer is no. No, H2SO3 is not amphiprotic. H2SO3 is not amphiprotic because, one, it is not water. It also doesn't have a negative charge. So it has no negative charge, so it's not amphiprotic. Now let's look at these two right here. Now we have two very, very similar, or actually the same, things right here. We have HSO3 minus plus water and another HSO3 minus plus water. And two possibilities could happen here. So one, HSO3 minus here can donate a proton and make, again, H3O plus, and since it donates a proton, that'll become SO3 minus 2. Okay, so since this donates a proton, this is a acid, and that would make this one again the base. Okay, because it's accepting a proton. Now let's take a look at this right here, HSO3 minus plus H2O again. Now this time let's have H2O donating the proton. And so if H2O donates a proton and loses one of its hydrogens, it'll become OH minus. And this will become H2SO3. And so that means H2O donated a proton, and therefore this is the acid. And HSO3 minus here accepted a proton, and therefore this is the base. Okay, so which ones are amphiprotic? Well, let's just take a look. Something that can act as an acid or a base. Clearly, H2O can act as a base here, and H2O can act as an acid. So amphiprotic here is H2O. Now, something else that can act like an acid and act like a base. Well, HSO3 minus can also act like an acid, and HSO3 minus can also act like a base. So HSO3 minus is also amphiprotic. Can act like an acid and can act like a base. Now, can H2SO3 act like a base? So let's take a look if we can make H2SO3 act like a base. So if H2SO3 acts like a base, what we'll make is H3SO3 positive. Now this is positive right here, and it can't do that. It can't accept another proton. There's nowhere for it to really attach to here. So H2SO3 can't be accepting protons, and therefore cannot act like a base, because, well, things that usually act like bases, things that are amphiprotic, must have a negative charge here, unless it's water, of course. Water is the big exception. And since H2SO3 doesn't have a negative charge, this reaction right here is not really possible. It's just H3SO3 plus is just too unstable, and therefore it is pretty much impossible for that to be created. So our amphiprotic substances in these examples right here are H2O and HSO3 minus.